In this video, I am going to discuss gravity assist and the orbital reversal maneuver. This is from the Appendix C of the book. You can buy the book by just scanning the QR code, which is like just below. Okay, so gravity assist is it's like almost seems like magic because normally when you think of a spacecraft and it's approaching a planet, so it falls into the planet's gravity well, and then you think that okay, if the spacecraft wanted to exit, it'll have to burn fuel, so it is going to lose velocity when it exits the gravity well. Um, However, falling into the gravity well of a planet be can actually increase your velocity of the spacecraft. When it exits, it'll have a greater velocity than it started out with. And also, if you burn fuel while you're in the gravity well, you'll get more velocity for the same amount of fuel, and that's the orbital effect. But in this video, I'm just going to talk about gravity assist. Okay. Now, so gravity assist is a maneuver, uh, and it uses the gravity of a planet or other celestial body to alter the path, which can also be very useful if you can change the direction and change the velocity of a spacecraft. It can be used to accelerate or decelerate a spacecraft. And why would you like to decelerate a spacecraft? Well, if you're sending a spacecraft, when it reaches the destination, you need to slow down to just make a landing at the destination, or if you want to do an orbit around a particular celestial body, you may need to slow down. And to do that, you can either burn fuel or you can use gravity assist to slow down your spacecraft. So both accelerating and decelerating require fuel, unless you're, of course, using gravity assist, which can be helpful. Okay, so I actually, when I was writing the book, I was kind of like trying to calculate how long it would take to get to Alpha Centauri, and one of the things I realized is that gravity assist can actually give a huge boost to the speed of the spacecraft and thus cut down the time taken to reach your destination. And I couldn't really find any good source of understanding gravity assist, something which can be explained in like 3-4 pages. And so what I finally did is, I'd taken my engineering entrance exam when I was 17 years old. And so I did remember, like, I remember mechanics and I remember calculus. And I also did a couple of courses in engineering, in mechanics and calculus while I was studying engineering. So anyway, I had to figure it out myself. I did not really get any good source. I'm sure there are lots of sources. I could have bought a textbook and I could have gone through like 100 pages, but I didn't want to do that. I wanted to kind of get to the point. And So I figured out this gravity assist, and I also put it in my book. Okay, so when you think of gravity assist, and you are actually the first thing to start with is an understanding of Keplerian orbits. Uh, so when a body when a spacecraft or an asteroid or something approaches a celestial body, which could be a planet or a star, and assuming that the mass of whatever is approaching is much smaller than the celestial body, it can have different kinds of orbits. If it is what is called captured by the celestial body, then it will have an elliptical orbit, which is this red orbit that you see. Somewhere between being captured and not captured is this like a green orbit, which is a parabola. And so this is like the boundary of being captured. So even a parabola is unbound, so it will not actually orbit the celestial body, but it will keep going away. And the hyperbola is when it is not captured and it just experiences a change in direction, and it may experience a change in velocity. So when you think of gravity assist, and so how do you analyze it? Well, what you do is you have to understand about inertial frames of reference. Now, an inertial frame of reference is a frame of reference in which Newtonian classical mechanics applies. And interestingly, you can have I'm right now, let's say I'm in a frame of reference. I'm sitting on my chair. I'm waving my hands. I'm applying force to move around, nod my head, blah, blah, blah. Okay, so, and all this can be analyzed in this inertial frame of reference in which my room is stationary. So you can say the room is the inertial frame of reference. Of course, the Earth is moving at a velocity, and my room is sort of in the same frame of reference as the Earth. But the Earth is moving with respect to the Sun, and if you're approximating that it's moving in a straight line, it's actually moving in an ellipse, but approximate it's a straight line, then the Earth has a particular inertial frame of reference which is different from the solar inertial frame of reference. So when you have an inertial frame of reference, you can apply the laws of motion, the Newtonian laws of motion to it. For example, one example of it, like suppose you're in a plane, and the plane is like flying at like 1,000 kilometers an hour. And you're playing ping pong, also called table tennis. So there's a table tennis table in the plane, and you're playing table tennis with your friend. You will not be able to make out any difference in the game, as even though the plane is flying at a very high speed, it would appear to you just you're playing like on the ground, as long as the plane does not accelerate or decelerate. So as long as the velocity does not change, so you're in the inertial frame of reference of the plane, and you can't, and everything works the way it would work, like suppose you are on Earth. So the point is that the laws of motion apply unchanged in an inertial frame of reference. It does not matter how much velocity that inertial frame of reference has with other inertial frames of reference. So what you do know is that what are you going to use for gravity assist? The one thing that you're going to use is that in an inertial frame of reference in which the celestial body is stationary, so you can say it's, let's say it's a planet. So in the planet inertial frame of reference, the orbit of whatever the spacecraft is going to be either a parabola or a hyperbola, assuming that it is not captured by the planet. So that is the first piece of information you will use to understand gravity assist. That if you are in the planet inertial frame of reference, in which the planet is stationary, the orbit, and let's consider an unbound orbit where the spacecraft is not captured by the planet, the unbound orbit will be a hyperbola. Okay? Unlikely to be a parabola because that's just a marginal case. Okay, we'll just like talk about hyperbolas. Okay, so the benefit of doing that is that you don't have to do any calculus after that, because if you kind of look at how are these orbits, how were they found? Well, you can find them by solving the partial differential equation. As you come closer to the planet, the force changes, and the direction also changes because the direction of the force on the spacecraft is always pointing towards the center of the planet. Okay, so like over here, the direction was like this. Now over here, the direction is like this. So you don't have to solve those differential equations because you've already been told that it is a parabola. And it's a parabola that is symmetric around the center of the parabola, which is about here. So it is symmetric around that point. And using that will enable you to understand gravity assist without doing any calculus. Okay. So in the planet inertial frame of reference, you know that the spacecraft's motion is going to be that of a hyperbola. It could be a parabola, but it's more likely to be a hyperbola. The next thing that you do is, normally when you're thinking of the spacecraft, you really think of the solar inertial frame of reference, because the spacecraft has taken off from Earth, it's traveling towards, let's say, Jupiter. So the thing that you say is stationary in this frame of reference is the sun. However, to get to gravity assist, to understand gravity assist, you should change your frame of reference to the planet frame, the planet which is going to give you the gravity assist. Okay, and the planet, of course, is in an orbit around the sun, but you can, for the purposes of gravity assist, you can just assume that it has a uniform rectilinear motion in the solar frame of reference, which is referred to as IFRS, in which case you can define a new inertial frame of reference, which is the planet in which the planet is stationary. So I'm going to call that inertial frame of reference IFRP. P is for planet, S was for solar. Now define x-axis to be the direction of motion of the planet. So the component of the planet P in IFRS, which is the solar planet inertial frame of reference, its magnitude will be P, and the component along the x-axis will be 0. So the laws of motion are unchanged in the inertial frame of reference, like I said earlier. Okay, and then let's take a look. So here we are, and we have a planet here which was actually going in this direction in the solar inertial frame of reference. But moving on to the planet frame of reference, this planet is stationary. And if this planet is stationary and you have a spacecraft approach it along this line and then get deflected, so its actual path will not, of course, be straight lines because it will be slightly curved. But I'm just approximating it, drawing, I'm just kind of continuing the asymptotes. And then the point where they meet is the center of the hyperbola. So what you have by moving to the inertial frame of reference for the planet is that you have the path of the spacecraft, and which you know is a hyperbola. So let us say that initially the path of the spacecraft, the asymptotic path, was at an angle theta with the direction, with x-axis, and x-axis is the direction of motion of the planet. Of course, in the inertial frame of reference of the planet, the motion of the planet is actually 0. So let's say it was at theta, and then after passing by the planet and having its direction change, the direction is phi. You have to, there's a certain amount of, shortcut you can use. Let's say you know that it's a hyperbola, so you can avoid the calculus, but you still have to be precise. You have to be precise about everything you say. Otherwise, classical mechanics explains a lot of things. It is very precise, but it's also very unforgiving. You can't make any mistakes in setting it up. Okay? Then what you do is you have your velocity of the spacecraft in the solar frame of reference, and then you want to change those to the planet frame of reference. And when you do that, these are the new velocities in the planet frame of reference. In the new velocity for x along the x-axis will be whatever it was in the solar frame of reference minus px, where px is the velocity of the planet. Similarly, the y component of velocity will be the same as the y component of velocity in the solar frame of reference, because we have set the planet's motion along the y-axis to be 0, and similarly for the velocities after gravity assist. Okay. Now, with all this, you can next set up the equations, and the details are in the book, so I'm just going to kind of skim over this. And what you get is that the initial velocity along the x-axis is given by this formula, and uh, the final velocities along the x and y axis will be given by these formulas. And this is solving for the situation where you're getting a gravity assist from Venus, and the gravity assist was, I mean, the velocity of Venus was 35 kilometers per second. And using these equations, I plot the sample gravity assist for various angles. Like, you know, you can, like when theta was 45 and then phi is 15, so that's the first one that I have. So theta, that means that this approached it at a 45-degree angle, and after gravity assist and the asymptotic, the direction of asymptotic travel was at a distance of 15. So the net deviation would have been 45 minus 15, so this would have been 30. And when you crunch the numbers, what you get is that the gravity assist is 2.75 kilometers per second. The velocity of the spacecraft is 46.44 kilometers per second. So it increases therefore to 49.19. That's not a very big increase, okay? And now, why did I say that the velocity of the spacecraft was 46.44? That was because the spacecraft was assumed to have been assembled at a certain distance from the sun and then sent in an orbit which was towards Venus. And similarly, for different theta and phi's, you get different amounts of gravity assist. For example, let's say theta was 0 and phi was minus 90. No, sorry, phi was 90. Then the deviation would have been minus 90. No, sorry. If theta is 0 and phi is minus 90, then the deviation is 90 degrees. So in our graph, what we have is theta to be 0. That means it was moving along this line. And then the deviation was minus 90. So the phi was minus 90. So it means that the spacecraft came this way and then it went this way. It went down in the negative direction. And the deviation then was 90 degrees. And the gravity assist turns out to be minus 9.6 kilometers per second. So the spacecraft approaches the planet from behind. It gets deviated. It just kind of starts going directly downwards. And it loses 9.6 kilometers per second. So that means that it has actually lost velocity. And this is the braking effect that you could also achieve from gravity assist. Okay, we also have this other situation. In this situation, the spacecraft was actually approaching the planet from behind, and we had a small increase in gravity assist depending on the angles, or a significant fall in the velocity from gravity assist. Okay. We can also look at a situation where the spacecraft, if this is the direction of the planet's movement, the spacecraft actually comes in towards the planet. The x component of the spacecraft, x component of velocity of the spacecraft, is actually negative. Like it comes in like this, let's say, and then it swings back swings around like this. Now, if you have done this, then by reversibility of orbits, you can actually get the results for this situation also. But I'm just going to kind of look at the situation separately. And here, I'm taking this angle to be theta and this angle to be phi. And I have a table, and then the new equations will give you that the initial velocity along the x direction must be this, and from that you can calculate what the final velocity in the x and y directions will be. By solving that equation. And in this table, we have this for different thetas and phis. And what you observe is here, you're actually getting substantial amount of gravity assist. So gravity assist results in an increase in velocity if the spacecraft is actually approaching the planet, and then it kind of swings around. One common way to think of it is you throw a ball at a cricket or a baseball bat, and the bat hits the ball, and then the ball speeds up. So if a ball is coming in, and the bat is also, they're approaching each other, after collision, the ball is going to rebound and go off at a greater velocity, and the velocity is going to be greater the greater is the speed of the bat. So you can look at it from and the change in velocity is going to be greater if the impact is elastic. And because in the elastic collision, there is no energy wasted as heat. Now the question is that gravity assist is actually an elastic collision. It is very similar to an elastic collision. And you're thinking, but there was no collision. It just sort of swung by, right? Now I'm going to show you where the collision actually occurs. So you have the spacecraft which is coming in, and then it's kind of being attracted by the planet, so it's sort of speeding up. And then once it gets behind, this planet is now, the spacecraft is actually now being pulled in this direction by the planet, right? Just like when a bat hits the ball is given a force in its opposite motion, direction of motion, of its initial motion. Similarly, the spacecraft in like all these points experiences a gravitational force which is going to make it accelerate in this direction. So that is the, sort of like a collision, but because they never touch each other, there is no energy wasted as heat, so it is like an elastic collision. And of course, because the distance when it is in this part of the orbit, this distance is a lot less than, let's say, this distance or this distance. So the force is also, it may seem like this is like a small part of the orbit where the spacecraft experienced a force which had a component in this direction, but because the distance was less and the force increases as is inversely proportional to the square of the distance. So there's a considerable amount of force. And so this is like it is analogous to the spacecraft being smacked by the planet and being deflected and going off in the other direction. So I just sort of crunched the numbers. I call this the orbital reversal gravity assist maneuver. And the idea here is that, let's say you assemble a spacecraft at, let's say near the Hector asteroid or Jupiter or somewhere. So like, more towards the outside part of the solar system. You assemble it. And then if you reverse this direction of motion, so then it's going to come down. And then it's going to, if this is the orbit of Venus, then it's like 2 is the orbit of Venus. So it's going to approach Venus in the other direction from which Venus is traveling. And just like a ball when it's hit by a bat, if they're traveling in different directions, you're going to get the ball is going to experience an increase in velocity. And that is what the goal is, to increase the velocity of the spacecraft so that it can get to its destination faster. Now, what happens if the ball and the bat were moving the same direction? Well, that's what is called bunting in baseball. Bunting, the batter really wants to slow the ball down and just wants to make it drop. So when the ball is coming in, the batter does not go forward to meet the ball with his bat. What he does is he starts withdrawing the bat, and then the ball hits the bat and then sort of like this drops. Same thing here. If the spacecraft and the planet were moving in the same direction during the time of gravity assist, initially if the spacecraft was moving the same direction as the planet, then there's likely to be a fall in velocity. Just like when a batter bunts a ball in baseball, okay? So some other this was actually this spacecraft was assumed to have been assembled from the Jupiter Trojan 624 Hector. Now, why Jupiter Trojan 624 Hector? Right down there. It explains all that in the book. And so if you now 624 Hector is traveling the same direction as Jupiter, is traveling the same direction as Venus, the same like in this figure, they're all traveling in the clockwise direction. So you actually have to reverse the orbit of Jupiter. Whatever you assemble from Jupiter Trojan 624 Hector, you have to reverse its direction to make it instead orbit in this direction if you want to get that gravity assist benefit. And then the question is, okay, instead of going through all this trouble, why not simply take this Jupiter Hector 624 and add that velocity that you would add delta V and send it towards its destination. And then if you do the calculation, what you find is that so after you've done gravity assist, also there is a loss of energy by the time you exit the solar system, because you're moving from the orbit of Venus to a point which you can say approximate to be infinity. So there is an increase in the potential energy of the spacecraft, which is paid by the loss in kinetic energy. And doing all those calculations, what you find is that the spacecraft is going to exit the solar system where its potential energy has gone from negative to approximately zero at a speed of 63.54 kilometers per second. Instead, if you took so you had to like use some delta V to reverse the orbit of the spacecraft. Right? Instead, if you just added that delta V to the spacecraft, what you would have at the time of exit from the solar system, only 26.66 kilometers per second. So there's a very significant increase in velocity at which you exit the solar system. And besides velocity, gravity assist can also be very useful in pointing your spacecraft in the right direction. Okay, so like I said, I was going through I was trying to figure out gravity assist, and I went through a few different sources, and I was a bit surprised why at the amount of mistakes there were. And basically I looked at 4 sources, and they were like, I think,
okay, this is something that's hardly ever explained, and that's why we have these explainer videos. Cool. So here's the answer. It turns out if you approach a planet from behind, okay, there it is orbiting the sun, right? And you approach it from behind in its orbit, right? Not only will the gravity pull you in, but you will gain speed just to catch up with the planet in its orbit. That makes sense.
If you approach a planet from behind, you are very likely to lose velocity. That's just like a ball being bunted. The bat and the ball traveling in the same direction. The planet and the spacecraft, if they're traveling in the same direction, then also the impact of gravity assist is to reduce the final velocity magnitude of the spacecraft. Okay, so this is MIT open source, and here what we see is the professor was calculating the final velocity for the spacecraft, and let's see.
We have VI minus twice gives us a plus the Saturn velocity, and that equals minus gives us a plus the final velocity of the spacecraft. And then we have 3 minuses here, so that gives us a minus the Saturn velocity. And we know from the problem that the initial velocity here of the spacecraft was actually given at 3 Saturn velocities. So we can tally this up now. We have 3. We have 3 plus 1 is 4, and we'll put this over on the other side. That gives us 5. 5 Saturn velocities equals our final velocity. So
okay, the problem here is that the components need to be considered separately. There is an x component and a y component, and that's Wikipedia. You know, what does it have to say? Well, again, here it says to increase speed, the spacecraft approaches the planet in the same direction the planet is orbiting the sun. No, most of the time when you approach it in the same direction, as we saw in our table, you lose velocity and departs in the opposite. To decrease speed, the planet approaches the spacecraft approaches the planet traveling the opposite direction from the planet's orbital velocity. No, this actually increases speed. Let's just edit it. Let me get rid of this error. Okay. Okay. And now we have somebody who does get it right, and that is Scott Manley. And he has a very popular YouTube channel.
So yeah, this is a very simple diagram. Now, many of you will immediately get confused because the coordinate system is backwards, and that's because if you look down on the planetary system of the Earth or Kerbin from the North Pole, then the planets move anti-clockwise.
These numbers are correct, and you can plug his numbers into the equations that I have in my book, and you will get those answers, his answers. Okay. Okay. So and with that, I will end this video, and I encourage you to buy the book to get the details. The QR code is here, and I'll see you in a later video.